Welcome to a lesson with Dr. Powell. We're going to look a little bit more at what we've just been seeing, which we call implicit differentiation. Notice that we did not explicitly solve for y before we started differentiation. That's why we call it implicit differentiation. Okay, so let's begin with an example here. Suppose we have something like y squared times the cosine of xy plus 3xy is equal to 5. So we have some kind of curve going on here, and we want to compute the slope of it as a formula in terms of x and y. So now to do this, we're going to use a little bit of technique. So we're going to think about repeating boxes in a boxing method. In other words, we're going to first of all, we'll take a box. We see a repeating box here. Everything else will be held as a constant on this side when we take a derivative, but we'll just think of those. But since it's repeating, we can think about that in tandem as being variable and everything else constant, and that's fine. Likewise, we can do the same thing with all the y's. Remember, y's are actually functions of x here in this particular case. And so when we take a derivative with respect to it, you know, maybe like right here, think of this as a composition. When we that'll turn into a multiplication and we'll get a dy dx. In fact, in every single term that we do when we do the y as a box that's repeated, we'll always get dy dx's. Let's see why that's useful. Okay. So let's think about 1 as being the x's and 2 as being the y's as a box. All right. So as a box is box. So in this case, when y is a box, like I mentioned, we're going to end up getting a dy dx popping out in every term. So we're going to have like a dy dx we can factor out of everything. Then we'll have something else over here. And to solve for dy dx becomes extra simple. So this is going to be equal to, over on this side, taking the derivative, we'll get 0. So we just subtract that over and divide by that bit, we get our formula. It'll be very nice. Boxing rule is very beneficial in this particular scenario. Saves a lot of time and hassle, and we can check our work to make sure we're doing it correctly as we go. So for x, okay, so let's assume that everything's constant in this whole left side except for where the x's pop up. So over here, but then remember we're going to be adding the other thing over there. So let's see. So that would be derivative of cosine is negative sine. So we get a negative, and y squared is like a constant, say. But notice that we're plugging something. So this is kind of like, we kind of had the cosine of something and of like xy, where we thought of y as being a constant. So this is like a 4 times x, like a 4x. So we need to take the derivative of this, which would just be, if it were 4, it'd be 4x would be 4, but since it's y, it'd just be y. Derivative of this would be the constant y times, okay? So times the derivative of this, which we already did, negative sine. So we end up just getting times y right here. Okay, next. Okay, so good for there. Then over here, we think of 3y as being a constant, x is the variable, so we just get 3y. Again, thinking of, you know, y as being like 4, so you'd have like 12x, right? Take derivative, you get 12. Well, that was just 3 times 4 or 3 times y, so 3y. We're done with that bit. Okay, let's move on to the next part. So with the repeating y box everywhere. All right, so in that case, where we think of everything else as being constant. So doing that, we end up getting, notice we have a product rule. X is thought of as a constant here. So we end up getting 2y, but every time we do something with the derivative, we'll always have a dy dx because y is like being plugged into that thing and y is a chunk in of itself. So we'll have to always multiply that because of this composition idea of something going into squaring. So when we take the derivative of y squared, that's what we're going to get. We're always going to have a dy dx under this line. Just helps us remember that. We know we're doing it right if we do. So if we take the derivative of that, we get this. But with a product rule, then we have a cosine xy not taking derivative, but then we add to that y squared not taking derivative of that, but then the cosine this time. So we end up getting negative sine of xy, but multiplied by the derivative of the inner part, xy. So x is thought of as constant, so it'd be like, the derivative would be x. But then we have to multiply by dy dx because it's like we were plugging a chunk in. So, well, derivative of x times y, so if you have 5 times a function, the derivative is simply 5 times the derivative of the function. I mean, we're using the same idea. So in that case, we're going to get, but replacing 5 with x itself. So we get, so we're going to get x times dy dx. Make sure we get that dy dx every time and every term. Okay, so we just did the product rule for this part right here, but then we have to take the derivative of this. 3x is considered as a constant, and so the derivative would be 3x, but then we have to multiply by dy dx since we're taking with respect to x, but y is now a chunk. So then we have plus 3x dy dx. So good, we have dy dx's in every term, so we know we kind of handled it in the right way. So then that's going to be equal to 0 in the end, the derivative of that side. Okay, so here it is. We can actually read it off from this line. Dy dx then is equal to, so we subtract this part over, so just make it negative or reverse the sign. So y squared sine of xy, y minus 3y, and then divide by dy dx factored out of all of that. So just 2y cosine xy. Then we have minus, and then we have a y squared x. So we could just do xy squared sine of xy. And then we have a plus 3x. And we have just successfully solved for the slope dy dx implicitly. The boxing method was very useful because it grouped things very nicely for us. Thanks for watching.